Nice to see you. Very good. Nice to see everybody. I look forward to getting to fields hopefully soon, but I'm really excited we still get to do it this way. So yeah, the material I'm talking about today is joint with Kyle Gannon and James Hansen, and I'm going to be talking about Keesler measures. So I'll just briefly say what a Keesler measure is and list some things, some titles from previous literature. So in general, a Keesler measure on a first order structure, say M, is just a finitely additive probability measure on the definable subsets of the structure in some fixed tuple of variables. Okay, so these are finitely additive measures on definable sets. And this nomenclature, calling them a Keesler measure, comes from sort of an early paper by Keesler on measures and forking. But of course, measures are around in other places in model theory as well, non-standard analysis, pseudo-finite counting measures. And more recently, there was a lot of work, more recently than 1987, I mean, there was a lot of work studying sort of Keesler measures in their own right, and also looking at the class of Keesler measures as an object itself, and finding various applications. And I've listed a whole bunch of papers here. And the thing I want to emphasize with this literature review is that there's this focus on the NIP setting, Keesler measures and NIP theories, and stable inside of there as well. And so this talk is going to be about looking at the behavior of Keesler measures outside of the NIP setting. And again, with this idea of looking at Keesler measures all at once as something to study in its own right. Okay, so let's go to the context. I'll be working with T, a complete theory. I'll be using U to denote a monster model, so very large, sufficiently saturated, sufficiently homogeneous model of the theory. And I'm going to be focusing on Keesler measures over the monster model. So I'll let MXU denote the collection of all Keesler measures, so all finitely additive probability measures on the Boolean algebra of definable subsets in these variables with parameters from the monster, parameters anywhere. Okay, and so when looking at Keesler measures for the first time, I think one usually notices that one usually makes this remark that you can think of the type space, the stone space of types, as sitting naturally inside the space of measures, because a type itself is a 0-1 valued Keesler measure, 0 if the formula or if the definable set is not in the type, and 1 if it is. And then another way of looking at that is by just sort of a basic topological fact. Any Keesler measure mu can uniquely determines a regular Borel probability measure on this stone space. So first you identify formulas or definable sets with the Clopin sets, and then use regularity to get the whole measure. And so then from this perspective, you can think of the types as just being like the Dirac measures at points, putting all the weight at one point in the stone space. And so then more generally, we have all these other measures to look at. Okay. Good. So once you have this picture of the types as special cases of measures, then the natural thing to do is to start taking things that you like to study about types and asking how those things work in the setting of measures. And so there'll be several pieces of the talk that are motivated by that pursuit. Right, and so the first notion that we can take from types to measures is the notion of an invariant measure. So I say that a Keesler measure mu is invariant over some small set A of parameters. So A is small relative to the saturation of the monster. So it's invariant if for any formula phi x, y, so I have my object variables x and then I leave some parameter variables y, and any tuple b that I can take from the y variables, the measure of the formula I get by plugging in that tuple depends only on the type of the parameters over this set A. Okay. And so then a different way to rephrase that is by defining these functions on type spaces. So if you have a measure mu, which is invariant over a small set A, then given any formula like above, I can define this function on the space of types over A in the y variables to 0, 1. And so what does it do? It takes a type of some parameter B and sends it to the measure of the resulting formula when I plug that parameter in. And so to say that the measure is invariant over A is precisely just to say this function is well defined. And I'm using this notation that Kyle taught me. So this is F, he calls them fiber functions, so F phi mu. But if you're thinking about the analogy to types, these are the corresponding object to defining schema for invariant types. Okay. And so then one thing that makes the study of measures in like the tame setting, say in the NIP or stable setting, one thing that makes that study work very well is that you can recognize model theoretic properties of tameness by the behavior of these functions. So for one thing, sort of a classical result is that if the theory is stable, then whenever you take an invariant measure like this and you define this function, it's always a continuous function for any formula. And so if this happens for a particular measure, we say that the measure is definable over the set A. And if you run this definition with the case of a type, you'll see it agrees with the usual definition, the one that Martin had in his talk. Okay. So in stable theories, all invariant measures are definable. Okay. And in NIP, you get something similar. So if the theory is NIP, then whenever you take an invariant measure like this function, this fiber function is maybe not continuous, but it's always a Borel function. So it's still pretty well behaved. It's not just some arbitrary function. Okay. And so if this happens for a particular measure, if you have a particular invariant measure and you always get a Borel function whenever you take any formula, we call the measure Borel definable over A. All right. Good, so using definable types, definable measures, Borel definable types, Borel definable measures, etc., you can do a lot of things, a lot of useful applications. And so one thing I'm going to talk about on the next slide that's nice when you have this Borel definability condition is that it gives a very easy, uniform way to define the Morley product of two measures. So let's look at that, recall that definition. So let's fix a measure mu in variables, say x, and then another measure nu in variables y. And I'll assume that the first one, mu, is Borel definable over some small set, whatever. Okay, and then what I've put on the definition here is what we want to do is define a product of these two measures. So we're defining mu times nu. It's going to be a measure in the variables x, y. And how do we do it? So we take an arbitrary formula in these variables, phi x, y, with parameters from somewhere, then pick a small set A that witnesses Borel definability of the measure mu and contains all of the parameters for the formula phi. So sort of A sees everything that's going on. And then the product measure, mu times nu of this formula, is obtained by integrating this Borel fiber function over its domain. So the Borel fiber function for mu with respect to the other measure nu, or at least restricted to the small set A. Okay, so here we're treating this other measure nu as a regular Borel measure on this stone space. Okay, so this via integration, but basically, I mean, you don't have to remember it precisely, but by integrating these Borel fiber functions, you get a nice way to define the Morley product. So this is called the Morley product of these two measures. So this is well defined. It doesn't depend on the choices of things we made in here. And it does generalize the usual Morley product of types if you run the definition. And then one thing that's not too hard to check is that if my second measure nu is also at least invariant over some small set, then so is the Morley product. So the Morley product sort of easily preserves invariance whenever you can define it. And then I should say that, like, we assumed that this measure is Borel definable. This is kind of a strong assumption. We made it so that you could always write down this integral without worrying about it. So that's one of the nice things about having a Borel definable measure. But of course, that's not strictly necessary. I mean, you could have a well-defined integral here for other reasons. For example, if the second measure nu is a type, if you're integrating with respect to a Dirac measure, just a type, then you can always define this as long as this function exists. So if the second measure nu is a type, you do have a well-defined Morley product with any invariant measure. And you can then very quickly get off into just defining more specific things, but we're going to stick to this Borel definable assumption as kind of a nice way of always being able to define this Morley product. Okay. Right, okay, so then, right, so back to the NIP setting, Hrushevsky and Pillay proved that every invariant measure is Borel definable, so you don't even have to worry about it. And so it's, again, easy to kind of prove that the Morley product preserves invariance. And so as a consequence of that, you get then that in an NIP theory, Borel definability is preserved by the Morley product. So if the Morley product of two Borel definable measures is again Borel definable. That's a very convenient thing because you don't, again, you just continue not even having to worry about it. You can always define them. These Morley products, you can continue taking Morley products of all kinds of invariant measures, everything you want. And so then that naturally raises the question of associativity for this operation. And some very basic elementary questions to start with. And so in the NIP setting, you can further prove that the Morley product is associative. But what's funny is that, in fact, there wasn't a complete proof of this in the literature. It was noticed there was kind of a hole in the argument, and so this is something that Kyle and I proved last summer, kind of as a precursor to this bigger project with James. But it is true. In an NIP theory, the Morley product is associative.
Oh, Gabe?
Yes.
Oh, yes. Okay. So what's the connection between Borel definability and invariance?
Thanks. Yeah, okay, so Borel definability implies invariance sort of by necessity. I mean, you could try a different definition if you want, but the way I defined it, it's a property of these fiber functions here, which only exist if you're working with an invariant measure. So every Borel definable implies invariant is the answer to your question. And for NIP theories, the other direction holds, which is one thing that makes it so nice. So invariant measures are always Borel definable. Okay, so going back to these two very basic questions, if you just read them, you know, okay, it's plausible that you wouldn't need NIP for either of these things, which would be great. So is this always true? Is Borel definability preserved by the Morley product in any theory? And if so, then do you always have associativity? And so both of these facts were sort of claimed or at least conjectured kind of in the folklore to hold for arbitrary theories, but there were no proofs. So when Kyle and James and I were thinking about this project of understanding Keesler measures, the behavior of Keesler measures and arbitrary theories, this was sort of the obvious first thing to try to understand. Like, is this actually true? How do you prove it for an arbitrary theory? So that was sort of the starting point for this project. And in the talk, I'm going to be giving you just a few examples of some results from the paper, but I wanted to start with this very first basic one. Okay, so the first thing we did in trying to prove this is just sit down and say, well, let's try to prove it, see what happens. And what you can prove is that things work as long as you assume enough stuff is countable. So this was our first result. So if you assume that the theory T is countable, and then you take two measures, mu and nu, over some variables, I don't care, and I assume that they're both Borel definable over some countable parameter set A, then you can make it work. So then the Morley product is again Borel definable over that same set. So that's good. And then if I take a third measure, lambda, whatever I want, I have these two products and they're equal. So I have associativity. Okay. So I wouldn't necessarily say that this theorem, the proof of this theorem required, like, I don't know what to say about it. I mean, it's long. It requires a lot of calculations, but nothing extremely, like, terribly sophisticated beyond sort of basic stuff from measure theory, in particular, approximation of Borel functions by simple functions, of course, and really where countability comes in is that it allows us to have sequences of things all the time, and we can just keep applying the dominated convergence theorem everywhere we want it over and over and over again. And so that's the first thing to go when you remove these assumptions that things are countable. I mean, we would like this to just always be true without assuming countability. And the first thing that breaks in the proof is that we can't apply the dominated convergence theorem anymore. And so then on the one hand, that makes you think, well, maybe I can take sort of a canonical failure of the dominated convergence theorem and turn it into a counterexample. Or maybe that's just a red herring and I can, somehow use any kind of clever trick you want that you're familiar with to, you prove it for countable the situation, and then somehow you use maybe local formula by formula or whatever to reduce to the countable situation, and then prove it in general. And so it wasn't really clear to us for a while how those two things were going to go. And then eventually we found out that it's sort of like bad news that in fact there is a counterexample in a fairly straightforward theory. So you need to assume something like countability in that theorem. And so our counterexample was in this theory T of the so-called generic ternary relation. So I'm just taking a language with a ternary relation symbol and taking the Frise limit of all finite structures. So I'm not adding any graph axioms or anything like that, just all structures to make it easy. And so in this theory, we prove that in fact the Morley product of arbitrary Borel definable measures need not be Borel definable. And in fact, this isn't even true for types. You can have the product of two Borel definable types be not only not Borel definable, but you can then construct a measure so that the Morley product with that measure just doesn't exist. So it can be like arbitrarily bad. And in fact, this refuted something that was claimed in the literature. So this was one of the reasons why we were hoping it wasn't going to happen this way. Okay, and then the bad news continues in this theory. We also showed that the Morley product doesn't necessarily need to be associative. And now, okay, if you have a failure of the product of Borel definability being Borel definable, you might be able to get a failure of associativity just by having measures that aren't well defined if you try to associate the parentheses one way. So that does happen, but in fact, we proved more. Even when all of the measures you have are well defined and even Borel definable themselves, associativity can fail. Okay, so and now of course this is all over uncountable parameter sets because of the previous theorem, but it is kind of bad news that you can't just do whatever you want with Borel definable measures and arbitrary theories. You have to be careful. And another bit of sort of bad news is that, again, this is not a very complicated theory, both in its definition and in its neostability. It's how large is the uncountable set? I think we take one that's the size of a type space. So in our examples, it's, I guess, continuum is the smallest that would come out of our proof. You might be able to make it smaller just by, I don't remember, but we take a parameter set that has a bijection to a type space over any model you want. So, okay. Right, so as I was saying, this is a super simple theory of rank 1. So, okay, it's not NIP, it's not stable, but it's very, it doesn't have as much, it doesn't have too much else going on. And so, so the one thing that we can make a remark on, the one place where you could kind of get your fingernails under there and try to get some leverage is the fact that we did need a ternary relation in this. A binary relation, or say the random graph, this would not work. So we definitely needed the ternary relation, and I think it raises what could be a nice question: is that can you get two dependent theories to behave nicely? Can this happen? Or put it another way, can these kinds of failures in this theorem happen in a two dependent theory? But I'm not going to say anything more about that. But as far as I can see, it's maybe the only dividing line that could be wedged in between this very nice theory and yeah, so binary theories, I think binary theories, we made some partial results, especially for types, things work out, at least in the first one. For measures, it got a little, anyway, we could talk about it another time. But yeah, start with binary theories. And I think there I would say it should work. And then two dependent, I don't know. Okay, right, so, okay, so then now I wanted to say one more thing about, now why does this not happen in an NIP theory? So Kyle and I gave this proof of associativity. And so we were interested in kind of trying to isolate that behavior as well and seeing, well, what, if I don't always get, say, like associativity for Borel definable measures, is there something I can assume beyond NIP that will give it to me? And so we did prove what I like this result. So let T be an arbitrary theory. And suppose I take three measures, mu, nu, and lambda, again, over whatever variables. And then I make some assumptions. First, I'm going to assume that mu, nu, and mu times nu are Borel definable. So I'm just assume I'm not in that bad situation. Now we know that associativity with lambda can still fail, so then I add a definition, I add an assumption on lambda as well, which is that for any small set A, the restriction of lambda to A has some other global extension, lambda hat, which is definable possibly over an entirely different parameter set, and it commutes with these three Borel definable measures, mu, nu, and mu times nu. So it looks like a strong assumption, and I'll discuss it in a second. But if you make this assumption on lambda, then you can prove associativity. Okay, and all right, so we get associativity if your measure lambda has this kind of strong behavior, but this can happen. So what's the sort of easy example where you would satisfy this? If lambda is a type, then you can do this. So let your lambda hat just realize, be a realized global type where you take a realization of the restriction to a small set. Then this is a definable type over that realization, and it's easy to show you can commute with anything if you have a realized type. Okay, so if the third measure is actually a type, then everything's okay. But this particular example here is also a very special case of what makes it work in NIP theories. So I'm not going to give definitions here, I just want to say this, but in an NIP theory, you can apply this theorem because you always have these smooth global extensions of measures over small sets. And again, okay, takes a little bit more work, but it's still pretty easy to show that smooth measures are definable and commute with anything as long as the measure is well defined, the product's well defined. Okay, so this theorem can be seen as a generalization of the NIP case to sort of exactly isolate what makes it work. Okay, so I guess I have 4 minutes left, and I wanted to say one more example. I mean, it's a big paper, there's a lot in the paper, but I wanted to give one more example of something that we proved about measures and arbitrary theories that get at this same kind of an idea of getting away from the NIP setting, but isolating exactly what is it about NIP that makes things work. So I'll just see what I can tell you about in 4 minutes here. And so the setting is, again, we're going to take a notion that's known and loved for types and move it to measures. So it's the notion of a finitely satisfiable measure in a small set. So a measure mu is finitely satisfiable in some small set A if any formula, possibly with parameters anywhere, if it has positive measure, then it has a solution in this small set. Okay. And it's a fairly easy exercise to show that if mu is finitely satisfiable in some small set, then it's invariant over that set. So we're back in the setting of invariant measures. It's another strengthening of invariance. And so what I'm going to be talking about now is about the interaction between definable measures and finitely satisfiable measures. How do these things interact? And there is a nice proposition, which maybe I'll skip the proof of, but okay, so there's a nice proposition which says that if you have a definable type, P, and then you have a finitely satisfiable in some small set measure nu, so a definable type and a finitely satisfiable measure, then they commute with each other. Okay, and I think I'll skip the proof. I wanted to just say though that this is if you were teaching a course, this would be like a nice easy homework exercise to get people, accustomed to these definitions. It's a very elementary proof to see how these things work. But when you look at it, when you look at this proposition, you automatically wonder, why am I assuming that this definable type is a type? Why not a measure? And so this then leads into another kind of fundamental important fact about NIP theories. So this was proved by Hrushevsky, Pillay, and Simon, which is that if you assume that you're working in an NIP theory, then you can replace the type with a measure. So if you have a definable measure, mu, and a finitely satisfiable measure, nu, then they commute when the theory is NIP. Okay. And so this proof is interesting because one, it's not like an easy homework exercise like that proposition was. And it also doesn't really go through that proposition. It kind of works differently. And in particular, their proof, they first used the fact that in an NIP theory, any Keesler measure can be like, I'm being fishy here, but Borel locally, whatever that means, approximated by types in its support. So they use some approximation results for Keesler measures and NIP theories to actually reduce to a different case. They reduce to the case that nu is a type, so that the finitely satisfiable measure is a type instead of the definable measure being a type. So it's like the opposite of that proposition. Okay, and then even in this case, they still have to do more work. It's handled via a similar approximation of mu by type. So they use this approximation method in both steps. And so I'll finish up just say what we did. So first thing that we did is we showed that you do need NIP for this result. So there is a complete theory T, a definable measure mu, and a finitely satisfiable type Q that don't commute with each other. So even this reduction to when nu is a type can fail if the theory is not NIP. And unlike the previous counterexample, this is a much more complicated theory. I'm not even going to get into its definition. And so then I want to just finish by saying the positive thing, what did we prove, is again, we kind of extracted, well, what makes NIP work? And what makes it work is the following thing. So suppose mu is a definable measure, and nu is a finitely satisfiable measure, which gives a well-defined Morley product. And then make another assumption about these restrictions. So assume that for any small set A, the restriction of mu has a definable global extension mu hat, possibly definable over a different set, that commutes with nu. Then mu commutes with nu, okay? So what's missing to get this commuting is, again, this kind of an assumption about other definable extensions of your measure. And so the last thing I'll say, well, one thing I'll say is that this proof is purely topological. It doesn't require any probabilistic approximation like the weak law of large numbers or anything from the NIP proof. Very simple. And it does include the NIP case because of these smooth global extensions that you always have. So it tells you why it works in the NIP setting, and it's a very nice elementary topological proof. Okay, so that's all I have time for. Thanks very much for your attention. I hope to see some of you again soon in person.
Thank you, Gabe. Let's all thank Gabe.